Hello, students. Welcome to today's session. Myself, Swayam. I'm currently pursuing my MBBS at IIMS Pune. So, we're going to discuss the part two of hydrocarbons today. Okay, we have completed part one of hydrocarbons that consisted of 16 questions. So, we'll do the rest 19 questions today. Okay, so let's start with the first question. Just a minute. Oh, so, the first question of today's session is question number 17. Okay. So it is asking the correct statement regarding the comparison of staggered and eclipsed conformation of ethane. Okay. So it is asking about the conformation isomer of ethane. So ethane has a conform if you write ethane this way, you can't know how many conformers are there. But if you draw ethane in this way, we had talked about this in the previous session also that in this sawhorse projection type of structure, we can fix a carbon and rotate another carbon so that the spatial arrangements of the hydrogen attached to this carbon will change according to the fixed carbon. Okay, so we'll get infinite numbers of conformers from a single molecule. Okay, of a single molecule. But we know, like, we have to know the two extreme isomers, that is one staggered and one is eclipsed. Staggered where the hydrogen atoms or substituted groups will be 180-degree apart, means they will face opposite to each other. Okay, but in the eclipsed form they will overlap each other. This is the eclipsed form of ethane. Eclipsed form of ethane. It is the sawhorse projection type. But we'll draw a new type of projection, that is Newman projection today, because today's question demands the Newman's projection. Let's draw Newman's projection. Newman's projection is like this is the fixed carbon atom. Like this whole circle is a carbon atom, that is back side carbon atom, and this dot is the front side carbon atom. Okay, and to this front side carbon, three hydrogen are attached, and to the back side carbon atom, three hydrogen atoms are attached. Okay, so this is the eclipsed form. Let's draw the staggered form. Okay, staggered form will be opposite direction, like 180-degree. All the bonds on the other carbon atom will be 180-degree in direction. Okay, so look at here. This is the staggered. Look. In these hydrogen atoms, this hydrogen atom and these hydrogen atoms are like very near to each other. Okay, very near to each other. So they will experience a repulsive force between them. Okay, and repulsive force means it is an unstable element. Okay, so due to the repulsive force, this hydrogen atom will like face some torsional force, like rotational force. Okay, easily rotational force. Due to that force, this molecule will be unstable, relatively unstable. But in this formation, the hydrogen atoms are very far away. Okay, 180-degree away, right? So they will face the minimum force of repulsion. Repulsive force, they'll face the minimum amount. So there will be the minimum torsional strain, right? So the this staggered form will be relatively stable. Okay. So the reason for stability, torsional strain. Okay. So instability. Okay. So let's read the question, options. The staggered conformation of ethane is less stable than eclipse conformation. No, the staggered is more stable. So option A is incorrect. The eclipse conformation of ethane is more stable than staggered conformation. This statement is also incorrect. Okay, because staggered formation is conformation is more stable. The eclipse conformation of ethane is more stable than staggered. It is also wrong. The staggered conformation of ethane is more stable than eclipse conformation because staggered conformation has no torsional strain. This is the correct option because staggered formation has the minimum or no torsional strain. Okay, so let's move on to next question. In this question, the correct option is D. You can see, take reference from this diagram also. Okay, same diagram. Which of the following compounds has the lowest boiling point? Okay, it is asking to compare the boiling points of different hydrocarbons. So first of all, I'll let you know the factor determining the boiling point. Okay, factors determining boiling point of hydrocarbon. The first and foremost uh, factor is molecular weight. Okay, the more the molecular weight of a compound, like just example, we'll take example. This will be easy. So let's take CH4, C2H6, C3H8. Okay, the boiling point is directly proportional to molecular weight. Okay, so in these three compounds, which will have the most boiling point, the highest boiling point, that will be C3H8. The order will be C3H8 more than C2H6 greater than CH4. Okay, so let's move on to the second factor. Second factor will be branching. Okay, due to branching of the hydrocarbons, the surface area will decrease. Okay, the surface area of a compound will decrease, and due to this decrease in surface area, the like the van der Waals forces or London dispersion forces will decrease among the compounds. Okay, so they will be loose. Okay, so they will be easily to evaporate. So branching is inversely like boiling point is inversely proportional to branching. Okay, and between alkene, alkyne, and alkanes, for the similar molecular weight, alkyne would have more boiling point. Least will be alkane. This is only applicable when all of the compounds have similar molecular weight. Okay. So in this question, let's focus on the options CH3, CH2, 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 CH3. Okay, let's first of all, we'll see the molecular weight. We'll focus on the molecular weights of the compound. And molecular weight of a hydrocarbon majorly depends upon the number of carbon atoms. So we'll count the carbon atoms here. For option A, the carbon atoms, number of carbon atoms are 5. Option B, number of carbon atoms are 5. Option C also have 5 carbon atoms, but option D has 4 carbon atoms. Okay. Here we can, here only we can decide which will have the least boiling point, because there is the option D having 4 carbon atom will have the least boiling point due to lesser molecular weight. Okay. So option D will be the answer. When hydrochloric acid gas is treated with propane, in presence of benzoyl peroxide, it gives. Okay. So there is a molecule propane. It reacts with HCl in presence of benzoyl peroxide. So you might be like wondering ki this will follow the electrophilic addition reaction. But here we are getting the peroxide alongside the HCl, so it will follow anti-Markovnikov rule. Okay, you might be wondering, but it is not the case here, because for peroxide effect or Kharas effect, only HBr has to be responsible, not HCl or HI. So this will go in the Markovnikov's rule. So if you see the mechanism here, it will break down to H plus and Cl minus. H plus will attack here and it will form a carbocation. The secondary carbocation will be more stable than primary. So secondary carbocation will be formed and chloride ion will attack this. So the final product will be 2-chloropropane. Okay, 2-chloropropane. Or else you can directly follow the Markovnikov's rule, like lesser or more, sorry, the more substituted carbon atom will have the final halogen. Okay, here the most substituted carbon atom is the middle one, so chlorine will be attached here. So option A is the correct option. Let's move on to question number 20. The restricted rotation about carbon-carbon double bond in 2-butene is due to. Okay, it is asking that why the rotation of carbon-carbon double bond in 2-butene is restricted. Okay, let's draw the 2-butene first. See, in this double bond, there is a sigma bond, that is head-on overlapping like this. Okay, head-on overlapping. And there will be a pi bond, which is like this. And this pi bond is not able to rotate. That's why the double bond is restricted. The motion of the double bond is restricted. Okay, so let's read out the question options. Option A: overlap of one s and sp2 hybridized orbitals. No, because here pi bond is forming. Overlap of two sp2 hybridized orbitals. No, there is pp overlapping. Overlap of one p and one sp2 hybridized orbitals. No. D, sideways overlap of two p orbitals. Yes, there is a sideways overlap of two p orbitals. That is why there is a formation of pi bond and the restriction of rotation. Okay, this is the basis for geometric isomerism. Geometric isomerism. Okay, because let's suppose This is a CH3. This is 2-butane. Okay. So as this bond is restricted, so if we move the methyl group here and hydrogen group here, so these two compounds will be different in their spatial arrangement because it can't form like it can't be converted to this spontaneously. These are two different molecules but having same chemical formula or molecular formula. So there will be a geometrical isomerism. We call these two as their geometric isomers. Okay, this is the cis form in which CH3 and CH3 are on same side. In this molecule, the CH3 CH3 are on same side, so it is a cis form. It is called as cis form. And in this molecule, CH3 and CH3 are 180-degree apart. Okay, so this form is called trans form. So option D is correct. Question number 21. The most suitable reagent for the following conversion is okay. So uh, one alkyne is converted into cis-2-butane. Which alkyne? 2-butane. Okay, 2-butane is converted into cis-2-butane. Let's see one by one options. Let's react one by let's react with 2-butane, CH3, C, C, CH3. If we'll give sodium plus like sodium in liquid NH3 like ammonia, it will give a transalkane. Remember this reaction. It will give a transalkane that is trans 2-butane. Sodium in liquid ammonia. If you react CH3C, CH3 with zinc HCl, it will give directly alkane. The hydrogenation here is not controlled, so it will directly give the ultimate product alkane. Okay, that is CH3, CH2, CH2, CH3. If you use SD2 plus H plus in H2O, there will be hydration reaction. Okay, so CH3, CH3, it will give Hg2 plus H plus H2O. It will give either a aldehyde or a ketone. In this molecule, as it has no terminal double bond, triple bond, it will give a ketone. Okay, so option B, let's use option B, CH3, C, CH, CH3. Let's suppose we will write the option B halfway, like H2, palladium. Let's write this much only. Then there will be the product will be an alkane. Okay, the product will be an alkane in this situation. But here it is given that quinoline is added. Okay, quinoline is also added. That means quinoline acts as a poison. It is a catalytic poison. So it reduces the catalytic power of palladium. Okay, so we'll get a controlled hydrogenation process, and this hydrogenation process will stop at alkene. It won't move to alkane. So the product will be an alkene. But which type of alkene? Cis or trans? This will produce cis alkene. But the sodium liquid NH3 reagent will produce trans alkene. You have to remember which will produce cis and which will produce trans. Okay, so it will produce C double bond C H H CH3 CH3, that is cis to butane. Quinoline is a catalytic poison. Reduces the power of palladium. Okay, so option B will be correct. Question number 22. Which one is correct order of acidity? Okay. How will you determine acidity of an alkene or an alkyne? Acidity of alkene and alkyne. Okay. So acidic nature of alkene or alkyne is directly proportional to the S character in hybridization of the carbon which it is attached to. Okay. So the more the S character is, the more the acidic hydrogen will get. Okay. So in alkyne, it is a sp hybridized uh, carbon. Okay. So the S character will be 50%. In alkene, that is CH2CH2, it is sp2 and here 33%. And in alkane, that is sp3, there will be 25% S character. Okay. So the maximum acidity, like acidic nature, will be of alkyne, then alkene, then alkane. But if there is a substitution, like if there is a additional CH3 molecule here, what will you do? How will you decide which will have more acidic nature, acetylene or propine? How will you know? You will know by removing the hydrogen atom. How? Let's compare CH3, like sorry, acetylene. Let's compare acetylene with propine. Okay. And remove the hydrogen. It will convert it into C minus CH. Okay. So the more the stability of carbanion produced, the more will be the acidic nature of the molecule, because it will be easier to leave the hydrogen atom. Okay, it will be easier to detach the hydrogen atom, right? So in which condition the carbanion is more stable? In the first situation, because these are same, but here a CH3 group is added, which will give a additional electron cloud towards the carbanion. Okay, so it will destabilize the carbanion. So it is more stable, so it will be more acidic. So what will be the order? That will be CH, then CH3, C triple bond CH, then CH2, and lastly alkane. So option A is correct here. Okay. Question number 23. Given there are given two molecules, 1 and 2 are okay. So let's study the structures. If you notice, In option A, the CH3, CH3, hydrogen, hydrogen, bromine and bromine are opposite to each other, are at an angle 180 degree to each other. So it is an staggered conformation. Okay. But in option 2, the bromine, bromine, hydrogen, hydrogen and CH3, CH3 are overlapping each other. So it will be a eclipse formation. So these are conformational isomers. Okay, these are type of conformers. So 1 and 2 are a pair of conformers. Okay, option C is correct. Let's move on to question number 24. HC acetylene reacts with NaNH2 liquid ammonia in presence of CH3 CH2Br produces X. X will react with NaNH2 liquid ammonia in presence of CH3 CH2Br will produce Y. What will be X and Y? Okay, let's react. HC. Let's okay. Firstly, we have to react with NaNH2 in liquid ammonia. Can you notice? It is a acid. It is a base because acetylene has a acidic hydrogen. So it will proceed like a acid base neutralization reaction. Okay. So and NaNH2 is a strong base. So the product will be a neutralization product that will be sodium Na plus and H2O. To this CH3 CH2 Br is added. CH3 CH2 Br is added. Okay. This will act as a nucleophile and it will attack the carbon atom here and it will be replaced. The bromine will be substituted by CHC minus. So the product will form as CH3 CH2 C triple bond CH. This is the compound X. The compound X reacts with NaNH2 and liquid NH3. So it will react with NaNH2 and liquid NH3. Okay. In this molecule also we have a acidic hydrogen. So NaNH2 will react with that acidic hydrogen here also. So what will be the product? CH3, CH2, C triple bond C minus Na plus. Again, we will add CH3, CH2Br to this. This whole anion will act as nucleophile and it will attack to this carbon and it will replace the bromine atom. So the final product will be CH3, CH2, C triple bond C, CH2, CH3. This is the final product, that is Y. Let's name this compound 1, 2, 3, 3-hexyne. The first compound name was X, that is 1, 2, 1 butane. X is 1 butane and Y is 3-hexyne. That is option number A. So option A is correct answer. Question number 25. Which of the following organic compounds has same hybridization as its combustion product? Okay, so that is CO2. Each hydrocarbon, when it undergoes combustion process, it will produce CO2 in the product side. So it is asking which organic compound among the four options has the same hybridization that of CO2 molecule. Let's find out the hybridization of CO2 first. Here the compound CO2. What is the hybridization of carbon here? that is sp hybridization. Okay, so basically it is asking among the four options which is sp hybridized carbon atom. So ethane, let's draw ethane, ch2 ch3 ch3. Ethane has sp3 hybridization. Ethyne, ethyl, it has sp hybridization. So the ethane or acetylene has the same hybridization as that of CO2. Okay, so option B is correct answer. But let's find out the hybridization of other two options also. That is ethene. Here the hybridization is sp2. Then ethanol, C2H5OH. It will also have the hybridization of sp3. So the correct answer is option B. Let's move on to question number 26. Which of the following reagents will be able to distinguish between one butane and two butane? Let's draw one butane and two butane. What is the difference between these two compounds? That is the position of the triple bond. In this, there is a terminal triple bond, and here it is intrinsic triple bond. Intrinsic triple bond. Okay. So it is asking which of the following reagents will be able to distinguish between these two. So basically, the concept is a reagent which will react differently with both of these molecules or compounds will give the distinguish, like we can distinguish by that reagent. Okay, so let's react the reagents with these compounds. Okay, first NaNH2. Okay, NaNH2, here B NaNH2. What will be the product? If we give NaNH2, just a minute. We'll see NaNH2 later because it is the answer. I'll say you the reason behind it, but let's see the other options so that you can appreciate the Na, like option A answer is the answer. So let's see option B. If you react HCl with this compound alkyne, it will react as a electrophilic addition reaction. Okay, electrophilic addition reaction. This will form dichloro compounds, dichloroalkanes. Okay, in these both reactions, the in the first reaction it will form 2-chlorobutene, and in the second it will form 2-chloro-2-butene. Okay, so these compounds are similar compounds, so we can't distinguish by the HCl by HCl. So we'll move on to option C, that is oxygen. Oxygen will oxidize these molecules, that is alkynes. It will also give the similar products. So it won't distinguish the two products given. Okay, so it won't be the correct option. So option D, bromine. What will bromine produce? Bromine will react with the first compound and it will form 1,2-dibromobutene. In the second, it will form 2,3-dibromobutene. These compounds are different but having the same properties, similar properties. So we can't distinguish between the two compounds with this reaction also. So let's see the option A, that is NaNH2. What will be the product in with NaNH2? NaNH2 look at this compound. This compound has one acidic hydrogen here. Okay. But this compound has no acidic hydrogen with this. Okay. It has an hydrogen. No, it don't have acidic hydrogen attached to the sp carbon, sp hybridized carbon. So if we react this compound with NaNH2, it will form a salt, sodium salt, because there will be a reaction of acid and base reaction, that is neutralization reaction. Because but this second compound, that is 2-butyl, doesn't have a acidic hydrogen. Okay, that's why it won't react with NaNH2. Okay, so we can distinguish between these compounds this way by the reaction of NaNH2 with alkynes. Okay, so option A is correct answer. Question number 27. IUPAC name of the compound. What is the compound given here? CH3, CH, double bond CHC, triple bond CH. Okay, so we have to find out the principal group first. If ENE and YNE are present, the principal group determining the number will be alkyne group. Okay, so here is the alkyne group present. So let's number the alkyne, like let's number the parent chain first. We'll go this way because this is the principal group. So it should have the lowest local number 1, then 2. Just a minute, I have drawn the wrong diagram. CH, no, correct. Okay, 1, 2, 3, 4, 5. So what will be the name? 1, 2, 3, 4, 5. Paint. Three in YNE. And there will be EN only, not ENE, because it is in the middle. So there will be EN, not EN. So the final name is EN. Yesterday we saw the numbering was according to the double bond side. Okay, why? Because the rule is if double bond and triple bond are present at the at the same position. Okay, like this molecule. See, if double bond and triple bond are present in this way, so we'll give preference to double bond for numbering. Okay, but in this molecule there is no such conditions. So option C will be correct. Base strength of CH3 CH2 minus, CH2 CH minus, HC C minus. Okay, so we'll see basic nature here. So how will you know basic nature of a compound? If a compound is willing to donate its electrons, that means it is a basic compound. Okay, so we'll measure the donation capability of these molecules. So let's see CH3, CH2 minus, CH2, CH minus, HC triple bond. The hybridization here is sp3, here is sp2, sp2, and here is sp. Okay, so with the increasing percentage of s character, we'll notice that the electrons will be attracted more towards the nucleus. Okay, so that means the nucleus, like the molecule, can stabilize the negative charge. Okay, so the more the stable carbon ion will be, it will have a decreased tendency to donate electrons. Okay, so here basic strength will be inversely proportional to the stability of carbon ion. Okay, stability of carbon ion. So here the most stable carbon ion is this, then this, then this. So the basic strength will be C, sorry, A, B greater than C. Okay, you can go in a alternative method also. These are the conjugate bases of some compounds, right? We'll add H, 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 and this will become the acid, the parent acid. So we know the more the strength of a parent acid, the weaker will be the conjugate base. The weaker will be the basic nature of the conjugate base. So here, what will like which will have the most acidic nature? CH2, CH2. So it will have the least basic conjugate base. In this CH3, CH3, it is the least acidic nature compound. So it will have a strong basic nature conjugate base. Okay. So option D is the correct option here. Options, sorry, 29, question number 29. A compound is treated with NaNH2 to give sodium salt. Identify the compound. NaNH2 is a strong base. It is like it reacts with a compound to give sodium salt. A salt is formed, that means it must be reacted with a acid. So we have to find out the acid from these options. A, C2H2, that is C triple bond CH. It is an alkyne, so it has acidic hydrogens. Acidic hydrogens. So it will react with NaNH2 to form a salt. Which sodium salt? CH double triple bond CH, NaNH2 will give CH triple bond C minus Na plus. Okay. C6H6 is benzene. It has no acidic character. C2H6 is a alkane. It will also not show acidic character. C2H4, it is an alkene. It is acidic, but it is not that much acidic that it will react with NaNH to form a salt. The only compound is acetylene, that is C2H2. So here the option A is the correct answer. Let's move to question number 30. Reduction of 2-butane with sodium in liquid ammonia gives predominantly. We discussed about this thing earlier. Today only, that 2-butane will react with sodium in liquid ammonia to give trans 2-butane. But when it reacts with hydrogen in palladium carbon in presence of which poison? Catalytic poison quinolone to give cis 2-butane. Got it? Cis product and trans product. So let's see question number here the option C will be correct answer. Question number 31. RCH2 CCl2R. So reaction chain we have to write RCH2 CCl2R reagent gives RC triple bond CR. Okay. Okay. So the hydrogen and chlorine atoms are removed from this molecule to form this. This is a dehydrohalogenation reaction. So dehydrohalogenation reaction is a feature of which reagent? You have to remember this. Alcoholic KOH. Got it? Aqueous KOH will form different element, but alcoholic KOH will form elimination product. Okay. So the reagent will be alcoholic KOH. Which alcohol? Majorly C2H5OH. So KOH in C2H5OH will produce the elimination product RC triple bond CR. Okay. So option C is the correct option here. The answer here. Let's move on to next question. Which is the most suitable reagent among the following to distinguish compound 3 from rest of the compound? So it is, the options are not given. So it is an incomplete question. So we'll leave it. Let's move on to question number 33. Which is the most suitable reagent among the following to distinguish compound 3 uh, from the rest of the compounds? Okay, this is the question. 31 question 32. Okay, so 32, the incomplete question is given here 30 in the question number 33. So let's see question number 33. Which is the most suitable reagent among the following to distinguish compound 3 from the rest of the compounds? So in the option A, it is given an alkyne. It is an intrinsic triple bond alkyne. Okay. In option 2, there is a given an alkene. Option 3, in terminal alkyne. Option 4, in terminal alkene. So you have to distinguish the terminal alkyne from the rest 3 compounds. Okay. So let's go one by one. Okay. Bromine and carbon tetrachloride. Bromine and carbon tetrachloride will react with option A to give addition product. Okay. With both one, like bromine, like I'll write this. Bromine in CCl4 carbon tetrachloride will give addition product with both alkene and alkyne. Okay. So it can't distinguish option 3 from option 1 or option 4. So it is incorrect. Option B, bromine in acetic acid. Same bromine but in acetic acid. It will also react with all the alkenes and alkynes in the same manner to produce addition compounds. So option B is also not correct. It won't distinguish between the two, like option, it won't distinguish option 3 from the rest of the compounds. Option C, let us see option C. Alcoholic alkyne KMnO4. Okay, alkyne alkaline KMnO4. It will produce purple color. Okay, it will react with all the compounds, but it will produce a purple color with each of them. So we can't distinguish here also. Okay, because it produces the same color. So option C is also not the answer. Let's see the option D, ammonical silver nitrate. This option, that is ammonical silver nitrate, it has a specificity. It only reacts with a terminal alkyne. Okay, ammonical silver nitrate. It only reacts with terminal alkyne. Okay, to produce alcohol, aldehyde or ketone. It will, like, you will study about these elements, or like about this reaction later in class 12th. Okay, so you'll know better there. The mechanism of the reaction will be taught there. So for now, you have to remember ammonical silver nitrate will not react with an intrinsic alkyne, that is the option one, or an alkene, but it will react with terminal alkyne to give aldehyde or ketone. Okay, so option D is correct. Solution bromine and CCl4 and bromine and CH3COH and alcohol, like alkaline KMnO4 will react with all unsaturated compounds. Okay, that is 1, 3, and 4. While ammonical AgNO3, that is silver nitrate, reacts only with terminal alkynes, that is option 3, and hence compound 3 can be distinguished from 1 and 2, like, and 4. This is the same explanation I gave. Question. Acetylenic hydrogens are acidic because, okay, acetylenic hydrogens means the hydrogens of acetylene, CC, acetylene compound CH. Okay, this is the hydrogen of acetylene. These hydrogens are acidic. Why? It is asking why. We knew these are the, like, these hydrogens are acidic because these are attached to sp hybridized at carbon atoms, so that the electrons here are more attracted towards or more closer to nucleus, so that hydrogen atoms will, like, can be easily detached from this compound, leaving a proton. Okay, this is the acidic nature. So let's find out that explanation from these four options. A. Option A. Sigma electron density of CH bond in acetylene is nearer to carbon. Yes, correct, because it is an sp hybridized carbon atom. So it will have 50% of S character, and it will, the sigma electron density will be more closer to carbon, like nucleus. Okay, so option A is correct. But let's see other options also. Acetylene has only open hydrogen in each carbon. No, it is not the correct explanation. Acetylene contains least number of hydrogens among the possible hydrocarbons having two carbons. It is also not related to acidic nature of acetylene. Acetylene belongs to the class of alkynes with molecular formula C and H2N minus 2. It is also not the correct explanation for acidic nature. The only option which is related to acidic nature and which is the reason of acidic nature of acetylene is option A. So the correct option is option A. So let's move on to the final question of today's session. The oxidation of benzene by V2O5 in presence of air produces. Okay, benzene. Let's draw a benzene ring. Benzene ring is very tough to break. Okay, it is not easy to break the benzene ring, but certain uh, reagents or certain compounds react with benzene and break it down to simpler compounds. In this reaction, we will see that only. Let's see the reaction. The oxidation of benzene with the help of V2O5. This you will have, like, you will have to remember. Okay, V2O5. It will produce a anhydride. Okay, it will produce a anhydride. What is the anhydride? It is another condition is the temperature should be very high for this reaction. It is not in that 10 degrees Celsius or 100 degrees Celsius or 200 degrees Celsius or 300, even 300 degrees Celsius also can't break the benzene. It will have to more than 410 degrees Celsius. Okay, for this reaction, we'll require minimum 410 degree Celsius temperature. So it will produce the compound that is CH, C double bond O, O, CH, C double bond O. Here, this is an anhydride form of malic acid, so it is known as malic anhydride. What will be the byproducts? That is decarboxylation products, that is CO2 plus water, two water molecules also will be produced. Okay, so the correct option will be option B, that is malic anhydride. You have to remember this um, reaction, that is oxidation by V2O5. Okay, you have to remember the conditions also, that high temperature, that is 410 degree Celsius. So your hydrocarbon chapters 35 previous year questions are completed here. Hopefully very new things also, and have revised the learned things. Okay, so you just have to practice PIQ more and more. If possible, you have to practice the JEE Mains PIQ also to grasp grasp the concept better. Okay, you have to prepare for the toughest situation. Then only you can score better in the tough exams also. Okay, so let's end this session here and go through the chapter again and prepare short note and revise. Okay, thank you.